Hello. Anybody wants to tell something? Okay. We'll start our class. Today, I want to start off with a new technique called root locus method. And before going there, somebody asked some question last time on the Routh-Hurwitz criteria. I hope I'm audible, right?
Yes, ma'am.
Ma'am, your voice is too low.
Oh, okay. I'll try to speak up. Is it fine now?
Yes, ma'am.
Okay, right. So last class, somebody asked some questions on the Routh-Hurwitz criterion, where why are we doing this operations? So, for example, I can start off with some example: a b s square plus c s power 1 plus d s power 0. Let us consider this as a characteristic equation, where characteristic equation is the denominator of a closed loop system. So we will get poles out of it, right? If this is a normal polynomial with order less than 3 or less than 3, we can straight away find the roots of this polynomial, that is the poles, so that we can say whether the system is stable or not. But in cases where the order is higher than 3, we need another method that then only this Routh-Hurwitz criterion came for the rescue. So we have a particular method to write this in a form where we will first start off with the odd degree polynomials, where I will write s power 3 coefficients of odd degree polynomial. So here the highest polynomial starts with 3. So whatever the highest polynomial, we will start off from here. So here it will be coefficients of s power 3, that is a, and s power 1, that is c. In the second row, this will be even coefficients of even polynomials. So this would be b and this would be d. So usually how we will do is, if this is a row and column, we will do a multiplication where BC and AD separately, and we will do a subtraction and whole divided by this element which is there in the lower first column. So this operation involves three different things. One is multiplication, individual multiplication, another one is subtraction, then division, right? So what this each operation means. First, we are multiplying separately, right? This is called cross multiplication, where we take two different rows and we do cross multiplication separately. So this will tell how much influence the each row has on the other row. And the next thing we are telling doing is the subtraction. This subtraction tells which one is dominant among this cross multiplication, whether this AD group is dominant or BC group is dominant. Why are we doing this is, our objective is not to find what are all the poles lies in the left of or right of. Our objective is to find whether any poles lies in the right of the S plane, because we just want to know whether the system is stable or not. So even one pole lies in the right of the S plane, that discards the stability. So from this sign change, and I can say which one of this is dominant. So if I know BC is dominant, I am going to say the output of this will be positive. If AD is dominant, the output of this will be negative. So when there is only positive lies, I can assure that there is no sign change. So nothing goes from left half of the explain to right half of the explain. So the system remains stable for the whole time. If this becomes dominant in between, so some poles changes from left half of the explain to right half of the explain. So I can say there is a sign change, so the system is unstable. I can jump to a conclusion using this operation. That's why we are doing this division operation is just to do the normalization. We don't want anything about the magnitude. We are just very much interested about the directions. That's why we are just normalizing it. There is nothing like you can leave it alone also, but to make it constant for all the steps, we are doing the normalization. I hope this is clear now. Why are we doing all
That,
this operation?
that means number of times the sign will change, there will number of RHPs.
Yes, that's why to know how much time the sign change or primarily is there any sign change, that's why we are doing this operation. Clear, right? I can move to next topic, I guess. If someone has
Then
any
what will happen if the
yeah,
one row will be zero, completely zero?
yeah,
One column means.
right. Um, you are asking ABCD. You are asking like this condition.
Yes, ma'am.
Okay. In this condition, we cannot determine whether the system sign has changed or not. So what are we going to do is we are going to replace this with the previous equation. This method has two different cases. The first case involves if only this element becomes 0 and it has some other x here. So in this case, since the first element only goes to 0, we can assume that the 0 is negligible to some other very small value, that is epsilon. And then we proceed with the same method and see whether the epsilon has changed sign in the upcoming steps. If it changed sign, we can claim that okay, some minute amount of pole location has been shifted to RHS, so the system might be unstable. But what if this both rows are changed to 0, 0? So this way we cannot determine in the case you asked. So we are going to choose the upper row, whatever information we have so far before making it 0, 0. So in this case, I am going to consider only the B and D row. So with this, I am going to construct another auxiliary equation where this auxiliary equation will be start with s square, right? This row starts with s square. If it is s power 4, this becomes b s power 4 plus d s power 2 equal to 0. Since in our example, this is s square. In our example, this is s square. We are going to write this as b s square plus d s power 0 equal to 0. This is our auxiliary equation. You have to find the roots for this auxiliary equation. Then you will replace this, you have to divide this auxiliary equation using this to find the roots or the change in the position or change in the polynomial coefficients. So you will end up having 2bs plus some d will go to 0 equal to 0. So you will replace this here to continue with the step. Okay, then you will get something out of it. But here the important point is we cannot determine the change in sign using this columns sign as before, as we did before. We have to consider the roots of the auxiliary equation here since we replaced it completely. So if the roots of the auxiliary equation's roots will always be in the imaginary axis. So if the roots of the auxiliary equation is single pair, conjugate or the imaginary poles occurs every time in pair. It won't occur like only 2j or minus 2j. It will occur plus or minus 2j. So you have to see whether this is a single pole pair or multiple pole pair at the same location. If it is single pole pair, then you can say the system is what do you call
Marginally stable.
Yeah, marginally stable. If there are same pole pair different times or multiple same pairs lies in the same location, for example plus or minus 2j comma plus or minus 2j, same pair occurs at the same location, then you can confidently say the system is unstable because this will increase the oscillatory frequency and eventually this will add up the frequency and it won't let it be in the marginally stable region, it will push it to unstable region. So
One
same,
doubt, ma'am.
yeah.
If the poles of the auxiliary equation is plus minus 2j we can say it is marginally stable.
Yeah.
But after calculating the rest of the poles, if we can see that there is again the same poles, then the overall system is unstable.
Yeah, I'm saying in the auxiliary equation, see, we got the auxiliary equation as b a square plus d. Since the overall degree is 2, you will get maximum 2 pole pair, right? But sometimes if we get b s power 4 plus d square equal to 0, some d s square equal to 0, you will get 4 pole pair. You will definitely get 4 pole pair. At that case, if it is plus 2j plus or minus 3j, then it's marginally stable because two different pole pairs occurs at the imaginary axis. But unfortunately, if both the pole pairs are same, that is two pair lying at the same location, then this will push the system from marginally stable to unstable region. So in this case, you have to tell the system is unstable, not marginally stable. Is it clear?
Yes, ma'am.
Right. Okay. Okay, I will move on to the new topic. This is another important topic in your quiz 2 syllabus, that is root locus method. Okay. First of all, we'll start off with what is root locus method. So far, we have studied what are all the control systems method we have. Mostly the control methods, in a sense, we studied is PID controller. So we have some system, open loop system. Then we have a controller. It might be P or PI or PID, whatever combination we want to take. So this controller can alter the position of the poles so that we will get the desired output response. That's how this controller will be helpful in a system or in a closed loop system. Now, instead of changing the poles by manually changing the gains Ki, Kp, Kd, now we want to determine particularly at what location if I put the K value or if I change the K value to some value, how can I expect the system to give a desired response. This is one of the method we are using for is the root locus technique. There are many methods exist that can make use of both time domain specifications or frequency domain specifications. In time domain specifications, we are studying this method called root locus method. So
Your voice is breaking.
okay, like I wanted to say this this is a new method, root locus method. This will help us determine changing the values of gain. How can we get the desired output response? Is it clear now?
Yes, ma'am.
Okay. Now we know our transient response depends on the closed loop poles of a system. So transient response, in the sense, it will give you like this. So whether the system gives higher rise time or a lower settling time, or whether it is settling or not, everything depends on the transient response of the system. So in PID controller, we will manually change the gain Kd, Kp, Ki, so that we will get this desired response in whatever way we want. So similarly, we are going to see by changing how much these gains, we can get this desired response using this root locus method. If it is not clear now, I will proceed with the next steps. You will be able to understand, and we can discuss that further. And if you consider a system, for example, if you consider a system that is K divided by some S into S plus A into S plus B. So this system has no zeros. One pole is at the origin. Then this is a type 1 system, and two poles are in the left half of the S plane according to this system. So if I want to say I want a stable output out of the system, by doing the closed loop transfer function, you will say, okay, the system will be stable because there is no poles that lies in the left half of the S plane unless we determine the K value. Okay. So now I am giving another system. Now I am asking for which value of K this system will be stable. How will you determine? Will you change each and every value every time, like K equal to 1, K equal to 2, K equal to 3, and for which value this will give a stable output? Is it possible to do that within a finite time? It's not in general, right? So we need a method to quickly change the value of K from 0 to infinity, so that I can tell at this point of value the system will be stable, or at this point of K value the system will be unstable, or it might be stable for 0 to infinity for all the time. Yeah, what is your doubt?
Ma'am, can't we find out the value of k with the help of Routh-Hurwitz?
With the help of Routh-Hurwitz, yeah, you will be able to say, but this is another method that it will more than telling the stability, it will help you in many ways. I'm going to tell that also. I will differentiate how this is better than Routh stability. With Routh stability, you will be able to find the range of k value. That's correct only. I will proceed and you will understand what is the main difference between Routh and this root locus. Okay. Okay. The first point is, as we discuss, changing the k value, how your closed loop poles will behave or how your desired response will change. This is one advantage of this root locus technique. So the important thing is, yeah, that's that. As I said, how changing the k loop gain affects the location of the closed loop poles. That is the one advantage of this root locus technique. Plotted for how this technique will, how we will do this technique is that we will plot all the roots of the characteristic equation, that is the closed loop poles, for different values of k from 0 to infinity by changing the gain from 0 to infinity, that is k from 0 to infinity, and see how the loci arrives. Then from that we can say if it crosses the imaginary axis for this point it is unstable. If it doesn't cross, then we can say this system is stable. And by root locus method, the another advantage is that we can predict the effect of location of closed loop poles by varying this gain from open loop thing. For Routh-Hurwitz criterion, you need to find the closed loop transfer function, and then only you can determine whether the system will be stable for this range of k. But root locus can tell with the open loop poles or open loop zeros itself. This is another advantage when compared to the Routh-Hurwitz criterion. Now, let us take a closed loop transfer function that is a standard function we all see, that R of s is the input and Y of s is the output, G of s your transfer function, H of s your feedback. So, your closed loop transfer function for a unity negative feedback system can be written in this form, G of s by 1 plus G of s into H of s. So, while determining the location of the poles, we will look for the denominator. So, I will just equate this to 0. That is the characteristic equation. So when I equate this to 0, usually I will find the roots of this and tell whether the system is stable or not. Here, in order to develop some basic rules for the root locus, I am just going to take this one to the other side, that is G of s into H of s is equal to minus 1. So now we are going to write this G of s into H of s equal to minus 1 in terms of polar coordinates. If you know Z, that is Z in Z equal to A plus BA, that is in terms of complex numbers. We are dealing with complex numbers, right? S will be written as zeta, what is this? Sigma plus J omega. This is the S plane we are dealing with. It comprises of both real and imaginary coordinates. So this Z can be written in polar form as modulus of Z angle of theta. So we are going to separate this equation into two different forms. One is in magnitude form, another one is in angle form, right? To facilitate the process. First one is, if I determine the magnitude or modulus of this equation, then I will get modulus of G of J omega. I'm just replacing S with J omega. Only I'm considering the frequency, not the real numbers, right? So G of J omega and H of J omega, modulus of these terms equal to 0. Minus 1 modulus will be equal to 1, right? And if I find the angle criterion, you will see for all the odd values of minus 180 or minus 1, if you find the angle for this minus 1, you will see for all the values of for all the angles of minus 180 degree, minus 180, 2 into minus 180, 3 into minus 180, 5 into minus 180, 7 into, so all the odd values will end up having the same circle. What is your doubt, Dhruv?
How angle of GH became plus minus 180?
Yeah, that's what. When you see in a polar coordinates, this will be your theta, zeta, this will be your J omega, right? I will write in pen. So if you find a polar coordinate, then this will be your -1. For example, unit circle I'm considering. So whenever you want to end up in -1, you want to take from origin, this is -180 degree direction, right? To end up in a value that is -1 in a unit circle. So similarly, whenever you crosses this line, and if you want to come again to this, you have to complete one 360 degree of circle. That's how you are adding odd numbers of this one. So 3 into -180 will end up in the same value. You would have completed one complete circle. Similarly, -5 into -180 will be, you will be reaching in the same point. So for all the values of -180 degree, odd values of -180 degree, you will reach this point. For all values of even 180 degree, that is plus 180 degree, 2 into 4 into 6 into, you will reach this one point. So we want only -1. According to our characteristic equation, G into H is equal to -1, not 1. So we are interested only in -180 degree. That's why we are considering this. And for every odd multiple of -180, you will end up in the same location, -1, -1. That's why we are considering this angle criterion as 2q plus 1. This is a general representation of odd numbers. Whenever you put 0, 1, 2, 3 here, you will get a odd number outcome here. That's why. So q can vary from 0, 1, 2 up to whatever the integer value we consider. Up to infinity it can vary, right? Is it clear now? This is the angle and magnitude criterion we are going to use throughout this method. So it should be clear in that. If you have any doubt, just ask me.
This one, this I got. Like after magnitude that we equate to 1, we have written that GH equals to plus minus 180. How did we get that?
Okay, it is in a general form, not only to the one, because when we are considering one that is in modulus, it is in general form. That's why it is plus or minus 180. When you consider only for -1, it is more defined to -180 degree. Like modulus can be of -1 and +1, right? That's why when you are taking modulus, you are generalizing it. Is it clear, or you still have any doubt on that?
This one.
Okay, right. You can also try writing in this form. You will get the same equation this way. Okay. Okay, right. Now we got to know two important terms in this thing, that is angle and magnitude criterion. This is previous class. Okay. Okay, right. The next thing I want to tell is, if someone asks what is root locus in one word, how can you tell that? It's a path taken by the roots of the characteristic equation when k varies from 0 to infinity. This is a general information or general explanation about the root locus method. Root locus of any system will tell you when you change your k value from 0 to infinity, how the system propagates. That's it. Very simple, right? So based on that propagation, we will try to interpret whether it is stable or not. That is the second product of that method. The method itself doesn't tell whether it is stable or not. Okay. And another thing is, I want to discuss the rules or the steps for building the root locus. I will discuss these rules first. It will be vague at first, and then we will revisit those rules or steps using an example. Then you will get some clear idea about it. Okay. First rule is that root locus is symmetrical about real axis. It may or may not symmetrical about imaginary, but root locus is always symmetrical about the real axis. And rule 2 is, each branch of root locus starts from open loop pole 2 and ends at open loop 0. This is very important point. This might help you with 1 or 2 marks question. So you should know this by heart. It starts from open loop pole to and ends at open loop 0. Every root locus starts from open loop poles, ends at open loop 0. Why particularly this is starting from open loop poles and ends at 0? Why not from 0 to pole? Because if you have a system like this, right, this is open loop system. When you write a closed loop system, you will write it in terms of S plus A into S plus B plus K, right? If I consider a S plus some C here, this will come in S plus C. So this is a closed loop poles. Some zero is there I'm considering. Instead of considering no zeros, I'm considering 1 0 to explain it better. Now, when you are seeing this is open loop 0, become closed loop poles here. So the 0 that doesn't have any work with stability in open loop system has some work in stability in a closed loop system. So this is a important term that ends up while considering in the stability. So in this manner, when you change the k from 0 to infinity, it affects the consideration of this open loop 0 in the closed loop stability. So when you put k equal to 0 here, let's just imagine putting k equal to 0 here, then what you will get? K s plus c divided by s plus a into s plus b. There is no influence of s plus c here, right? Open loop 0 here. So when you are putting k equal to 0, it is the closed loop poles equal to open loop poles. Are you agreeing with this? Is everyone with me?
Yes, ma'am.
Right. Any doubt in this?
No, ma'am.
Right. Okay. I hope everybody is. Nobody has any doubts. So when the k equal to 0, your open loop poles and closed loop poles are 0. So your closed loop poles depend on only your open loop poles. That's why when k equal to 0, it starts with open loop poles. When k equal to infinity, so if I put k equal to infinity here, then this s plus a and s plus b terms have very minimum influence. This become very small. Only this k infinity into s plus c term has more weightage than the s plus a and s plus b. So then this will become closed loop poles. Or in other term, what I can say is open loop 0. This open loops 0 has more weightage than open loop poles. That's why when it is starting from 0, it is on open loop poles. When it goes to infinity, it ends at open loop zeros. So can you make this by heart now, like intuitively, why it is starting from open loop poles and ends in open loop zeros? If you understand, just give a thumbs up. Right. Rest of the people, Sanket, Prabhanjan.
Yeah, I can let that.
What?
Yeah, I can understand that. Thank you.
Okay, right. Good. So I'm proceeding with the rule 3. Rule 3 is having number of real axis open loop pole plus zeros. Okay, I am skipping this because it doesn't make sense without solving any rule. I can add up again. Okay, the point of intersection of asymptotes. I will explain what is asymptote. Just I'm writing it the rule here. We will revisit this at pole or whatever open loop poles we are considering. This will be sum of poles minus sum of zeros divided by number of poles minus number of zeros. Keep this aside for now. Breakaway and breaking points of root locus are determined from the roots of the equation dk by ds equal to 0. Okay. Right. For now, this is fine.
What is the sigma A you written? That numerator?
This which one here?
Sigma A, that rule number 3.
Okay, that is number of asymptotes. I will explain. Just writing
Yep.
the so that we can revisit it later. Okay. For now, this is enough. We'll stop at rule 4. We'll see some example. Then I will visit this and explain it properly. Okay. First, I will take an book back example. Okay. Example is, you know that this is loop transfer function, right? If we write only g of s into h of s, we called it as loop transfer function. G of s is open loop transfer function. C of s by R of s is, or y of s by R of s is closed loop transfer function. Okay, we are just writing g of s into h of s. Most probably, root locus method will give this loop transfer function because we are determining it for g into h equal to -1. That's why. Okay. The question tells this is the system k by s into s plus 2 into s plus 4. So they are asking us to plot the root locus and just plot the root locus for now. Stability and thing we'll see in the later example. First, see how to plot a root locus in a step-by-step method. The first step is that identify the open loop poles and zeros. Identify or locate open loop poles or zeros. So since this is a loop transfer function, it's again a open loop transfer function. We haven't done any closed loop or considered any feedback. So the open loop poles are s, s plus 2, s plus 4. That is 0, -2, -4. The open loop zeros here are 0. There is no 0. That's why it is 0. Okay. Right. So it has 3 poles and 0 zeros for now in this particular example. Right. This is the first step. The second step is plot poles and zeros. This helps us to visualize the system properly. So for our system, you know how to plot pole 0, right? We use x to represent poles always and zeros to represent zeros. The symbol to represent 0. Even in MATLAB, we use this. So one pole lies in the 0, another pole lies in -2, another pole lies in -4. There is no 0, so we are not marking any zeros here or circle symbol here, right? This is our pole 0 plot. So far, so good, simple, right? Now we are going straight into the root locus method. root locus method, the first like formal step of root locus method is to determine the what can we say, availability, or we are trying to determine whether the root locus exists or not. Right? This is the third step. For this, we have rules. What rule is that? If a pole or a zero lies right to a test point is odd, then root locus exists. If not, if same is even, then root locus doesn't exist. This is the rule for the step 3. For example, in our case, there are 3 poles, right? -2, 0, -4. Now I am taking a test point here. If I take a test point here, I am looking whether there is any poles or zeros to the right side of this test point. Is there any poles or zeros exist in the right side of the test point?
No, ma'am.
No. So root locus doesn't exist here. Now I'm taking a test point here. Then I'm seeing whether there is any zero exists on the right line. One exists, that is odd. So I'm considering exists here in this point or in this vicinity until it reaches the another poles. I'm considering root locus exists. Now I am taking another test point here. So if I consider a test point here, so this is T1, this is T2, this is T3. In T3, if I look to the right, there exists 2 poles, which is even. So next.
Not exist.
So I'm not going to consider any root locus here. I'm just telling that there will not be any root locus exist between this pole and this pole. No root locus, right? Then again I'm taking a, so this goes to infinity, just for your information, minus. Then again I'm taking a test point here, T4. When I look back, there are 3 poles, that is odd, so root locus exists. So I'm going to consider, since there are no other poles to the left of this, I'm consider until minus infinity from this point, root locus exists. So now you know, wherever I marked it as in black color, that is the place root locus exists in real axis. Important point is this tells in real axis only. We are not bothered about imaginary axis right now. So just in real axis we are testing wherever the root locus is existing. So whenever you take a test point and see where how many number of poles or zeros. Zeros also should be considered. Now if there is a 0 here, then this test point will say there is a root locus exists. Then this will be in the vicinity. That's how you have to measure it. There should not be any clash between zeros and poles here, right? It should be considered together. Why this is not going? Okay. Good. So this will also minus infinity, but it is an imaginary axis. This is the real axis. Good. Now third point, till third point, is it clear?
Ma'am,
Yeah.
ma'am, why it should be odd?
Yeah, it's like just checking. Then only there is a rule in root locus. Let's take. I'm just explaining it here. Rule is, if there are 2 poles, then the root locus will go from here. Like the root locus will separate from here or this direction or whatever direction angle might differ. If there is 2 zeros, then the root locus will come inside. So this is how the changing the k value will affect the loci of your system. It's proven based on the system's nature and by changing the k value, this is how the system behaves. If there are 1 0 and 1 pole, then there might be a branch or there might not be a branch. So you cannot say whether the root loci exists here or not. So based on this calculation, they have come up to the conclusion that sometimes if there is every time if there are any poles or zero x's in the right side, whenever you are taking a test point, if it is odd, then root locus exists. There might be some branches. It may go out or go in, or break out or break in. If it is even, there will not be any locus, because there will not be any changes in the loci of the system. That's why they have defined in that way. This point is going to be explained in later steps, so I'm erasing it from here now. Okay, step 4 is calculating the asymptotes. Now we are going to see.
And if there are two poles at a point, then we have to count 1 or 2.
No. Poles and zeros are same here. If there are 2 poles, you should count it as even only. If there
No,
are
ma'am. At point 0 there are 2 poles, then we have to count it as 1 or 2.
Oh, okay. It will be 2 only. Like you are telling at origin, if there are 2 poles, kind of a square.
Yes, ma'am.
It is 2 only. You should consider it as even only. If you take a test point here, it will be even. There will not be any root locus inside this.
Okay, ma'am.
Okay. Step 4 is calculate asymptotes, branches going to infinity. What are these asymptotes? Asymptotes show the direction of branches that go to infinity, right? So we say, right, when k equal to 0, it starts with open loop poles, and when k equal to infinity, it starts to open loop zeros. For some system, the poles can be here and zeros can be here. So you don't know whether the root locus comes like this or this or this, right? So to determine this angle, at which angle this root locus is going to propagate from open loop poles to open loop zero is determined using this asymptotes. This angle we are going to calculate here in this step. Okay, so now so this will be more helpful if the number of poles is greater than number of zeros. So there are 3 poles and 1 zero. How will you determine which pole will go to this 0? So this angle of asymptotes for each poles, if you calculate, you can precisely know which pole is going to end up in that 1 0, and which other 2 poles are going to go till infinity. So if there are more poles and lesser zeros, whatever number of zeros it is there, that many branches will start with poles to 0. Other branch will move to infinity. For example, if there are 3, I'm saying it starts from open loop poles to zeros, right? If there are 3 poles and 1 0, then 1 pole will go to the 0, another 2 poles will go to infinity. This is how it is. So if there are 2 poles and 1 0, one will go here, one will go to infinity. If there are 1 pole and 2 zeros, so this will go to one of the zeros, and one of the infinite, like asymptotes from infinity, will come to this 0. This is how the root locus will behave, right? Now the formula that I am going to calculate is, first of all, to find number of asymptotes, the asymptotes number will be equal to n minus m, where n is the number of poles and m is the number of zeros. This hash symbol represents number of, okay? So we have 3 poles and 0 zeros. So we have number of asymptotes for our particular example we took now is 3, right? The next formula for this is one. The second one is the centroid. So from where this asymptote starts, or from which point or which poles this asymptote is going to start. That's what have been calculated using this formula. That is sum of poles minus sum of zeros, that I already has given in the rule, minus number of poles minus number of zeros. For us, sum of poles is 0 plus minus 2 plus minus 4, minus of 0, no zeros, and 3 minus 0. So this will give you what you will get. Minus 6 by 3 will be minus 2. So your centroid will be, centroid for this particular pole will be minus 2. So from minus 2 pole, the asymptote will start to emerge. From this pole only the asymptote will emerge. And at what angles it will emerge? For this, there is again a formula. That angle can be given using this theta k equal to 2k plus 1, 180 by n minus sum, where k or k equal to 1 to whatever integer we are considering. So here it will be, so we already found 3 asymptotes, and the centroid for the asymptote is minus 2. So we can interpret from s is equal to minus 2, 3 asymptotes will go, or 3 asymptotes will emerge, right? So when you use this k equal to 0, it will be 2 into 180 by 3. This will give you 120, right? Okay, 180.
K is 0, so won't it be 180?
180, yeah, I missed it. It will be 180. When k equal to 1, this will be, sorry, 180, right? Sorry, it is 180 by 3, right? It will be 60 only. Because k goes to 0, 1 into 180 by 3, that is 60. When k equal to 1, this will become 3 into 180 by 3, this will become 180. When k equal to 2, this becomes 5 into 180. That's what I was saying, odd numbers comes to the same place. That's why we are using this. When you are using this formula, we have this. This will give you 300 degree. So this 3 asymptotes, since we have 3 asymptotes, I am stopping it with k equal to 2. If you have 4, I will calculate k equal to 3 also. Now we have 3 angles. So from s is equal to minus 2, 3 asymptotes will emerge at the degrees of 60, 180 and 300, right? So, so far we have determined in real axis what are all the ways, what are all the positions of the root locus, and we have found how the asymptotes or branch of this root locus will emerge from what location at what degrees. Right now we have these many informations, right? The next thing is,
From these angles are with x-axis, like the real axis.
real axis only, yes. This belongs to real axis. We are calculating it for real axis. Step 5 is finding the breakaway and break-in points. This is where I told if a root locus lies in between. If a root locus lies in between 2 poles, 2 adjacent open loop poles. Only I am speaking about open loop, not closed loop so far. Everything is in open loop poles. In the real axis, then there exists at least one breakaway point. This breakaway point will look like this, right? It might go to the zeros at the degrees that we calculated in this step. If it is 60 degree, it will break out like this. If it is 180 degree, it will break out like this, right? So that angle we have calculated in the previous step. So how many breaks or break-in we have, that is what we are calculating using the step 5. Now, this is first example. The second example, if there exists a root locus in between two adjacent open loop zeros, because when I take a test point here, I will have only 1 0 here, then this will be in the root locus. So if there exists a root locus in between two adjacent open loop zeros, then I can say the point in between this will act as a break-in point, not breakout. This is break-in, that both points towards the same direction, it won't go out. I'm meaning to tell that at least one breaking point will exist. Here also, at least one breakaway. It can be two or more than one, but at least one is evident here. Okay, then you can ask, what if there exists one pole and 1 0, or 1 0 or one pole? There also the root locus will exist, right? So in this case, you cannot guarantee whether the breakaway or break-in points exist. It might exist or it might not exist. We cannot comment on this. It has to be determined based on the number of poles, number of zeros, and while drawing the root locus, we will know whether there exists or not. But using this formula or the intuition, or in a 1 mark question, if someone asks there exists two adjacent one pole and 1 0, where there exists whether it is a break-in or breakaway, you cannot comment on that. You should choose cannot be determined or cannot be commented. Okay. Right. How to find this breakaway or breaking points? First, what this tells. This breakaway points where multiple branches leave or meet. When it is leave, we call breakaway. When it meets, it is breaking on the real axis. This is also in real axis. Between poles or zeros. Poles or poles, zeros and zeros also exist. So, why are we doing this? To know where the real axis branches diverge into complex planes. If there exists zeros or poles in a system, we should know at what point it is emerging into the complex plane, right? So, for example, if there is a zero here, if there is a pole here, so it emerges from poles to zero somehow. So somehow it has to cross this complex plane, right? So at what point it is crossing here? That also can be determined using this equation or this particular step. Okay, then how to determine this is d by ds of the formula to determine this is d by ds of g of s into h of s. And it is equal to 0. It is, again you can say g of s into h of s equal to 0, because if you take this term here, this will again be same. So we are just using g of s into h, d by ds of g of s into h of s equal to 0. So what, for our case, what is the equation? We have this, what do we consider? -2, -4, 0, right? So this will be d by ds of s into s plus 2 into s plus 4 equal to 0. And then this will be s square plus 6s plus 8 equal to 0, right? Any mistake I did? No, right? Okay, when you differentiate this, you will get 3s square plus 12s plus 8 equal to 0. So when you find the roots for this equation, minus b plus or minus root of b square minus 4 into 12 into 8 whole by 2 into 3, that is 6. Okay, you will have something like this. So when I consider, this will be, what is this, 6, 14, will be 48 by 6. This will give you minus 2 plus or minus root 48. How can we split this? 4 into 12 will work.
Yes, ma'am.
Yeah, then this will be 2 root 12 by 6.
4 root 3.
3. Yeah. Oh, no, wait. Minus 12 plus or minus 2 root. 4 root 3. Yeah, right. By 6 will give you minus 2 or minus by 3 root minus plus or here. These are all the two roots of this equation. If I didn't do properly, just let me know. Okay. So when you find, this will become minus 2 plus 2 by root 3 comma, just calculate this decimal point minus, these are all the 2 points. So you have to check if this points are in the root locus. Then if it is there, then if it is between two poles, it is breakaway. Two zeros, if it is break-in, or if it is between zeros and poles, you can consider whatever you want based on the number of poles and the number of zeros. So we will see examples for that. No need to keep that in mind right now. Okay. Can anyone check what are all the points? I will use the calculator and see. This will give you minus 4.4 and minus 0.59. Okay. These are all the 2 points you are getting out of this. So let's check whether minus 4.4 is in the root locus. Minus 4.4. Yeah, it is in the root locus. Right. Then the next point is, this is in the root locus, so this is a breakaway point because it is, we cannot tell it is over this. And minus 0.59, is it there? Yeah, it is also in the root locus, so this is also a breakaway point. Good. Now we found what are all the breakaway points. I'm just going to mention it here so that we can use it later. 1 pole, 2 pole, 3rd pole. These are all root locus areas. At minus 4.4, there is a breakaway point. At minus 0.59, there is a breakaway point. Good. Now, the step 6 is exhaustive, I know that, but when you practice doing sums, I think you can do it within 2-3 minutes, the entire problem. This is another stability check step, and it is not needed for all the sums, but if you need for some problems based on the questions, you can make use of it. Just letting you know that this step exists. This step helps to know the value of K. I was telling about the stability, right? So at which the system becomes marginally stable, because after this it will go to unstable, right? That's why we are determining this critical point when it becomes the marginally stable or poles at imaginary axis. Since we already found the breakaway and break-in point, this will be easy for us to determine. That's why we are determining why it is marginally stable. So always, again, the Routh-Hurwitz comes for rescue. So for Routh-Hurwitz, we will consider only closed loop poles. The information we have is g of s into h of s. For closed loop poles, we have to find 1 plus z, that's it, and equate it to 0. So for our method, it's k by s into s plus 2 into s plus 4 equal to 0. This will give you plus k equal to 0, s square plus 6s plus 8s plus k equal to 0. Perfect. Now when you find the route stability criterion, 1, 8, 6, k, then 48 minus k by 6, so it will be 0. Again 48 k into 48 minus k by 6, oh, k only will come because the other term is 0, only k. Right, now check how the system should be stable if there is no sign change. K should be greater than 0, so 1 point. Another one is 48 minus k greater than 0, minus k greater than minus 48, k greater than 48. So this will make a upper bound as greater than 48. So the system will be marginally stable after, the system will be marginally stable at k equal to 48. After that the system will become, I'm confusing. After
K less than 48.
yeah.
48.
Right. So at k equal to 48, the system will enter into the marginal stability. Right? For all values k greater than 48, it is stable. For all value lesser than that, it will become unstable. Now we are going to plot across this imaginary axis at this point, right? I'll just see whether we have determined it properly. Okay, now I said it goes from poles to 0, but we have 3 poles. There are 0 zeros, so there is no way the pole can extend to 0. So all the 3 poles are going to go to infinity, maybe minus infinity or plus infinity based on the location of poles and breakaway points, and all the 3 poles will be going to infinity, that we know. Now we are plotting the root locus. So based on all the information we have collected so far, at one moment. What point it is going? I think I have missed one point. Let me check it good. A square 3a square plus 2s. Okay. This will become marginally stable at 48. If k equal to 48, this term will go to 0. So considering k equal to 48, when it crosses the imaginary axis, I am going to see this k, right, s cube, s square. So far we have found at what point the root loci crosses the imaginary axis. Like when k equal to 48, it crosses the imaginary axis. But in imaginary axis, at what value it is crossing, we have to determine, right? That I missed. So when k equal to 48, this row becomes 0, 0. So here, when k equal to 48, this will go to 0, right? So I am considering the auxiliary equation right now. That is 6x square, what we do in Routh-Horvitz generally. So this will give you this. So a equal to dA by ds we will do, differentiate it with respect to the auxiliary equation. That is 12s equal to 0. So yes will be, am I missing something? Okay, sorry for confusing. Okay, just determine this. We are not going to find the root with that. K square is equal to minus k. So s square is equal to minus k by 6. So k equal to 48 right now. So 48 by 6. So s is equal to what this will give you 8. So s is equal to 2 root 2 j, right? So at this point, it is crossing the imaginary axis. Just I missed this point. Just please add this to that. Okay, now we know two breakaway points, one here, one here. So these two breakaway points will cross the imaginary axis at this point, minus 2 root 2j. So at degrees, there are 3 degrees we found, right? One is 60 from s is equal to minus 2, one is minus 60, minus 180, and minus 300. These are all the three asymptotes we have found. So this 60 and 300 will be going like this. These are all the angle of asymptotes the root loci will follow. And the another minus 180 is along this way. So this is the reference path. This is not the actual path the root loci will follow. This is the angle of asymptotes is the reference path. So from the breakaway point, this is the actual way it is traveling to infinity, crossing the imaginary axis to minus infinity, and from here this root loci will travel to infinity at minus 180 degree towards minus infinity. Is it clear? This is our final root locus diagram for this particular equation, and we found the stability will exist for values k greater than 48. In addition to that, if you change the k value from 0 to infinity, at what points the system is stable, at what points the system is from verge of stability, using the open loopholes we are doing here. That is what the important point that missed in the Routh-Horvitz criterion. For that, you have to calculate closed loopholes every time. So in order for a higher loop system or higher order system, or for many times determining the stability or range of stability using the open loopholes will be helpful. This is just another method, that's it.
Where is the minus 300 degree?
Where are you?
Where is the minus 300 degree? I think you marked minus 60 and minus 180.
Oh, this is
So
again minus 300. This is minus 60.
oh, okay.
Everything will be calculated in counterclockwise direction.
Yeah.
This, this is the general rule for finding locus of any system. So we can do multiple problems on this to make it clear and to get familiar with this method. So don't worry about this right now. Good. If you have any doubts, I will give you 2-3 minutes to think about it. If you have any particular doubts or any questions it came across your mind, just let me know. I will start up with some small questions based on root locus. Again, we will solve a big question in later classes. RL, I usually mean root locus, okay? This can be some intuitive questions. Okay, first question is, do you think about the doubts? Let me take some time to complete this question. What do you think it is correct? There are 4 options I have given. The question is, find the valid root locus diagram.
A should be the correct.
How can you tell?
Yeah, because of both on the top side and bottom side, it is from pole to 0,
Uh-huh.
and the pole is going to infinity. So
Why can't be the B? Okay, this can be easily neglected using the intuition because it goes from poles to 0. Always the root locus goes from open loop zeros. Sorry, this goes from 0 to poles. Always the root locus goes from open loop poles to open loop zeros. So this is wrong. This is wrong. Both are wrong. Out of these two, both are going from poles to zeros. How can you say whether it is? Oh, I haven't marked this. Okay, this also goes here. No. How can you say?
Ma'am, in B part, the pole is going to 0. That is, it should be stable because it's on left hand side. And A part, it should not go to 0 because it's on right hand side. It should divert.
You're telling this is not correct, this might be correct.
So because it is on left hand side, I'm going to 0 as well.
Okay, right. It's a good guess, but the correct option is option A. doesn't matter how the root locus goes. It matters where the poles and zeros lies. And why the option A is correct in the sense we have to find another one important thing that I didn't include, that this is only suitable for this kind of problem. That is finding the angle of departure of the particular root locus. So we can discuss this on the later side. Just to give a motivation for this, I have given this method. This, if you know the location of poles and zeros, we can easily calculate this. I will give that in the steps. Okay. Right. So based on that, if you find the angle of departure, you will see this is the correct angle that it takes, theta 1 instead of this. This theta 3 and theta 4 will be wrong. Okay. Then okay, they are asking, like they have given this equation. Second question would be, they have given this equation, a square plus 4s plus 4, 2a square plus 11s plus 30. This is very long equation, equal to 0, where k greater than 0. What are all the, or where the asymptotes meets. This is the another question. This can you find the poles of the system? Is it easy? Poles will be of s power 4. We already saw one method, right? We have to use that method. S power 4 plus 11s cube plus 30s square plus 4s cube. I might make some mistake. Please solve with me and tell me if I have done any mistake. S square plus 43, 120, yes, plus 4s square plus 44s plus 120 again, plus k square plus 4k equal to 0. So this will give you s power 4, 45 s power 4, this 2 is taken, s cube is 15 s cube plus 30, 44, 74, 78, 78 plus k into s square plus, to find, yes, 120, 120, 164, 164s plus 120 plus 4k. Is it right? Did I miss anything? S power 4, 11 is cube, 30 square, plus 4 is cube, plus 44 is square, plus 120 is 4 is square, plus 44 is plus 120. Okay. Remaining things are this. Okay, only one s power 4 is there, no? Why did I use 45 here? This cube is only 1. S square will be 30. 30. Oh, S cube will be 44 is cube. 15. Okay. Square is 30 for 74. 78. 78 plus k. Alright. Everything is considered. Now, yes. This over 120, 164, 164 is. So 120 plus 4. Okay, good. Now we have this equation. X power 4 plus 15 is q plus 78 plus k 10 square plus 64 plus 120 plus 4 equal to 0. They told k equal to 0. Sorry, k greater than 0. So considering k equal to 1, or how can we consider it? I'm going to use MATLAB. You can use the same method down.
Ma'am, can we make this equation in 1 plus
Yeah, you can
kg?
see a square is equal to x, kind of. You can simplify it to that.
No, ma'am, taking the first term in denominator and taking k s square plus 4 in the starting equation, like making it 1 plus k gs format.
No, we have to. No, this is the characteristic equation they have given. We have to take it in this way only. Oh, we can do. Are you asking in terms of this?
Yes,
Can take, right. That you can do. Yeah, that is also a simple step. I didn't think about it. That's right. That way you can find it easy, right? Instead of doing all these things. Yeah, very good. We can take it in terms of that. So this will become common denominator. If you take this s square can be s plus 2 the whole square. This will be 30. If you do what, it will give you 11. 5 and 6. So this will become 1 by, not 1. The above term will come here, right? K into s, k square plus 4k. This will become, okay, wait. Yeah, this is brilliant idea. S square plus 4, right? S plus 2 the whole square into s plus 5 into s plus 6. Good. Now we have poles easily. So the poles will be minus 2, minus 2, minus 5, minus 6. Good. The zeros will be minus 2j plus or minus 2j. Right? So finding the asymptotes will be easy. Sum of poles will be this minus sum of zeros. Sum of zeros will give you 0 divided by number of poles are 4 poles minus 2 zeros. So this will give you minus 10, 15 by 2 minus 7.5. Right? So your asymptote will go from the point s is equal to minus 7.5. That's the answer. Thanks for the hint. Good. So these are all some short problem we can see. We can I can come up with some bigger problems like solving step by step. Again, revisiting those rules and all. And if you have any doubts till now, you can ask me. Another small problem I can give. Again, a characteristic equation plus k just to strengthen the formulas. We are asked to find the centroid of this asymptote. What formula we used here? Sum of poles, that is the centroid, right? So what we found is the centroid. This is for another equation. We are going to do the same thing again. Just we will write this in terms of g of s by 1 plus g of s into h of s. Poles will be 0, minus 1, minus 2. So the centroid would be sum of this minus 3 minus sum of zeros divided by 3 minus 0, it will be minus 1. Centroid will lie at minus 1. So s is equal to minus 1. That's it. I'm giving a open loop transfer function s plus 3 divided by s into s plus 1, s plus 2, s plus 4. Can you find the angle of asymptotes? I will give you the formula. This is the formula. Theta k equal to 2k plus 1 into 180 divided by n minus m. Just see how many angle of asymptotes you need and put k accordingly. That's it. How can we solve this? They have given open loop transfer function, g of s. It is not loop transfer function. It's a unity feedback system. Since h of s is equal to 1, g of s into h of s equal to g of s only. So we can straight away consider this as a loop transfer function. Right? Okay. Now determine the poles first, then determine the angle of asymptotes. The poles should be 0, minus 1, minus 2, minus 4. 0 should be minus 3. So for sigma k will be 2q plus 1 into 180 degree divided by n minus m. This will be 2q plus 1, 180 divided by 4 minus 1, 3. Just substituting q, again you will get the same as we calculated before, right? That's it. So for different poles and different number of zeros, this angle might vary. Is it okay? Anybody has any doubt?
No, ma'am.
Ma'am, I am having one doubt.
Yeah.
Ma'am, when we take some point and see if there are odd number of points on the right side, In the lecture, sir has taken some 180-degree concept for the right side points. I didn't get that.
Okay. That it's a kind of different examples. Everywhere there are cases, right? Special cases for every methods. So it will come inside that. I'm going to take few special case problems in the next week. I can discuss that now. Since we are running out of time, explaining all the steps inside that would be difficult. No. So I'll keep this in mind. I will explain it in the next class. Okay.
For this MATLAB assignment, when is planned to release?
It's week 8 and week 9. I'm going to show some MATLAB example now. Just let me share my screen. I will tell you how to do it. It will be for week 8 and week 9. One problem will be from locus and one will be from board areas or compensate. Most probably.
So it will be released in the course page, correct?
Yeah. Will be released.
Okay. Yeah.
It will be released in 1 or 2 days.
Okay.
Okay. I'll just stop presenting here and I will present the MATLAB page. Okay, now I'm going to write, we are going to take the same example so that we can visualize how we have calculated, right? That is the question. Okay. Now I have put transfer function. K by S into S plus 2 into. How many of you are familiar with MATLAB? Or how many of you don't know MATLAB? Like, don't know, like only know basic commands, not so much.
We are familiar with the MATLAB in the signal and system course and in the DSP we have done.
Okay, right. Okay. Here it is. So when you find this S square, 2s, 3s, so s cube, 3s, and 2s, 0 will be. In MATLAB, this is very easy. Just a command that is R locus. You have to find. You have to put this first. This is a form of writing the transfer function. I am considering k equal to 1 for simplicity now. We can change this k and see how to locus varies later. And for this, that TF is the keyword. You can name it anything you want in the left hand side. Just telling for those who are new to MATLAB. So this TF is the keyword you have to use to write any numbers in terms of transfer functions. So this will make this first square box is the numerator and the second square box is the coefficients of the denominator. So if I write this in terms of polynomial, this will give you k by s power 3 plus 3s square plus 2s plus 0. Nothing will be there, so I'm considering 0. That's how I have written this. Instead of this k, I have written 1 for now. Let's visualize it for 1, and instead of this sq, coefficient is 1 and 3, 2, 0. I have written inside a square brackets. So the first square bracket is the numerator separated by comma. Second square bracket is the denominator. You can see the format or syntax here, right? Transfer function, numerator, denominator, and if you want to give some sampling time or any name you want to give to the transfer function, you can give. This is enough for simple steps. And if you want to plot and visualize the root locus, the keyword is R locus in MATLAB.
In denominator, why have you taken 1?
Numerator.
In denominator.
1 is the coefficient of s cube. Here, in this one you are asking? Is it clear or should I tell again?
Yes, now it's clear.
Okay, right. Now I'm running this MATLAB script. Okay, this is the root locus plot we have seen so far. Is it correct, like whatever we have done in our thing? It's correct, right? If you go to systems or properties, okay, I think it won't be possible, right? So this is the root locus plot. If you see closely, you can see the poles here, right? Is it visible? Like one pole is here. Oh, it is not there. I presented this on screen. Okay, is it visible now? Yeah.
Yes, ma'am.
Right. So this is the entire root locus plot. You can see that poles are mentioned using the x here, right? And this is a breakaway point that goes to infinity, and this is another breakaway point. It goes from one pole to infinity. This violet color, it goes from one poles to infinity, crossing the imaginary axis at 2 root 2 value. And the another pole comes to this breakaway point and goes to minus infinity, crossing at minus 2 root 2, right? And the another point starts from 0.44 and goes to infinity. That's it. So this is the root locus plot. You can do it in MATLAB assignment using this simple step. Whatever value you want to give, you can give. Like if I put 1000, did you find any change in the root locus plot now? No, because it is considering only open loop transfer function. There will not be any change by changing the k value, because the root locus itself is telling you when k value changes from 0 to infinity how it propagates, right? So just changing the k doesn't change the root locus plot. Here in MATLAB I'm whatever k value you are giving, it will consider that if some gain is there in the numerator, how it changes from 0 to infinity, how the root locus proceeds. That's how it plots. I hope that's clear. If you have any other doubts, you can ask. You can just play around this. You can try this for different systems and make sure whatever you are calculating by hand, it's coinciding with the MATLAB thing. Just you will be asked to, in later class, I think week 7 or 8, you will get compensator design. So for designing a compensator, we will use the help of this root locus or Bode that we are going to study in the next few classes. So the design assignment will be based on that. Design a compensator based on this. If we give a time domain specification, you should use root locus method. If we give a frequency domain specification, you should use Bode plotter. Time domain specification in the sense we will give rise time, zeta value or settling time, whatever is there in the time domain responses. For frequency domain, we will give phase margin, gain margin. So in that case, you will use a Bode plot to design a compensator. Clear? So why do we need compensator in the sense? So far we have changed the values of k to make the system respond in a desired way. So what if we add some poles or zeros? What if we couldn't make the system respond in a particular way only by changing the gains? We might need to add more poles or zeros. So how we can strategically add these poles and zeros to make the system work in a desired way? That's where the compensator comes in the picture. That's it for today. If you don't have any doubt, you can wrap it up. Is it fine? Can we wrap it up?
Yes, ma'am.
Right. Thank you.
Thank you, ma'am.
Thank you.
Ma'am, one doubt I am having.
Yeah.
Ma'am, actually, I was searching on net. Like it is saying that if one point is on right side of some point, it is taken as 180 degree, and if it is on left side, it is taken as 0 degree. Can you explain that?
Yeah, that is the
Explain the same thing professor is doing.
Yeah, that is the angle of departure we are finding that one root locus diagram I have given so that you are asked to find whether it is A or B, right? So it is based on the angle of departure. If it is in the right side, you have to consider this, like it is like if it is odd degree, in order to come to that same location, you will take minus 180 degree turn, right? So if it is even, it is 180 degree. That's how it is being calculated based on the position of poles and zeros. We can explain this better with examples. I can show you in the next class.
Yeah. Thank you.
Oh, it got